In recent decades, electric power systems have been transformed significantly due to deployment of computer and networking technologies. Although greater reliability and efficiency can be achieved, these technologies also bring new vulnerabilities that arise from the increasing complexity. Large disturbances, therefore, can cause cascading events, leading to a system collapse. Power system blackouts can make a severe impact on the economy and society. This was evidenced by several major outages, such as the blackouts in the eastern US and Canada in August 2003, India in 2012, Texas and Florida in 2017, and island-wide power outage in Puerto Rico recently. As a result, enhancing reliability of the power grids is a critical task. Power grid need to be operated at rated values, for example frequency, voltage. To achieve this, the power need to be balanced in real time, that is, the load demand equals to the power supply. Disturbances from a serious lightning strike to subsequent fire in a generator may lead to failures. These failures causes other generators to adjust in real time and may result into 1. Controlled system with normal operation, 2. Subsequent failures leading to cascading and blackout. The rated frequency in the US is 60 Hz. Through balancing the demand and generation, the frequency can be maintained stably. Point A represents the interconnection frequency immediately before the disturbance. Point B represents the interconnection frequency at the point immediately after the frequency stabilizes due to governor action but before the contingent control area takes corrective action. Point C represents the interconnection frequency at its maximum deviation due to the loss of rotating kinetic energy from the interconnection. Point D represents the interconnection settling frequency at 60 seconds after the point A. The left-hand side figure is the 179 bus system, which is a variation of the simplified model of the Western interconnection in North America. Loads and generation units are not evenly distributed in power grids. After the tripping of transmission lines, the system splits into two islands. The power generation of those generators in the right island cannot be injected into the left island. Therefore, there is an active power deficit in the left island, leading to the frequency drop. Figures show the frequency change as a result of the sudden loss of a large amount of generation in the southern WEC. Green is bus quite close to location of generator trip while blue and red are quite distant. As we know, the conventional UFLS has been in operation for decades. Settings are decided by offline analysis. There is no communication between relays. Usually, it is configured to shed excessive loads conservatively. For centralized UFLS schemes, optimization calculation is performed. Optimal load shedding decision can be achieved. Relevant information must be transmitted to a central processing facility. Delay of a measurement may result in a slow response of the global computational process. Optimization calculation may be time-consuming. For distributed UFLS schemes, the single point of failure can be avoided. The flexibility in the system extension is enhanced. Distributed computation can be utilized with information sharing. The amount of load to be shed may not be optimized for lack of global information. However, effectiveness is the goal. For example, quickly stop the frequency decay beyond a tolerance of frequency deviation. In the monitoring step, agents monitor both the frequency and frequency derivative. If abnormal conditions are detected, agents start communication to inform other agents and determine the total amount of load to be shed, that is, the total active power deficiency. In the distribution step, the load shedding amount is averagely assigned to all nodes. Each node knows the amount of load assigned to be shed by itself. Distributed load shedding amount should be determined quickly. The test platform for real-time simulation is shown. The real-time power system simulation is conducted in RTDS, which connects with 3 RIAPS nodes through the router. Simulation control is achieved by RSCOD. RIAPS Development Control Station is running in the VM VirtualBox. In the contingency scenario, the power grid splits into 2 islands after losing 3 lines and 2 transformers. Please look at the left-hand side figure. In the south island, there is 1 generator and an active power deficit exists. Without remedial actions, the frequency declines continuously, leading to a system collapse. The system response and load shedding results are shown in the lower figure and table. If there is no RAS, a system collapse happens, leading to the loss of all loads, 66 MW and 32 MVA. With the proposed RAS2 that runs on 3 RIAPS nodes, the frequency decline stops at 3.02 seconds by shutting 19.37 MW and 9.58 MVAR, respectively. In this study, the secondary control is not included. Thus, the system frequency does not recover back to 60 Hz. The blue curve is the NERC under. The system runs in normal condition. The rated frequency is 60 Hz. By clicking the button Apply Contingency, the power grid splits into 2 islands. Due to the active power deficit, the frequency of the south island starts to drop. The red curve is the dynamic simulation without RAS. The frequency continues to drop, leading to the system collapse. The green curve is the dynamic simulation with RAS. The frequency decline stops at 3.02 seconds by shutting 19.37 MW and 9.58 MVAR, respectively. In this study, the secondary control is not included. Thus, the system frequency does not recover back to 60 Hz. The real-time power system simulation is conducted in RTDS, which connects with 3 RIAPS nodes through the router. Simulation control is achieved by RSCOD. RIAPS Development Control Station is running in the VM VirtualBox. Data points are collected and saved for the offline simulation demo. The button Zoom Out helps with displaying the complete curves. By clicking the Zoom In, the recent data points are presented. The button Reset helps with resetting the system status back to normal.